Okay, please hold on. It's okay. Can you see? Okay. Okay, so we will start. We will start with our lecture today. Okay, we will continue from the place that we stopped yesterday. Okay, we are studying about AM modulation, so amplitude modulation. Okay, in order to have the modulation happen, so we need to have a modulator and also demodulators. Okay, so modulate meaning it will combine the signal. So demodulator it will separate the signal. So we need to have this modulator as a main component of AM or amplitude modulation. Okay, so we'll read a little bit. Okay, so AM modulator is used to generate amplitude modulated wave. Okay, so the function of AM modulator is to create a amplitude modulated wave. So there are two types of modulators we will use. So the first type we call as a square law modulator, and so this is the picture. So you have mini transformers. Okay, so we'll have non-linear device. So the difference between square law modulator and switching modulator. So in the circuit you have a non-linear device. So meaning it's not fixed. And for switching modulator we will use diode. Okay, so apart from that, the other circuits will be almost the same. Okay, so we'll see a little bit on the construction of both both type of AM modulators. Okay, we will see the square law modulator first. So you are taking a modulating signal. So you plus with your carrier signal. Okay, carrier signal. So you combine it in a summation unit. Then you are getting a modulated signal. So you pass to okay, sorry. So the modulator signal. So once you combine, you pass to square law device. So it will have some conversions and also some filtration in order to generate the modulated wave. Okay, so that's the function of square law modulator. Okay, so we just go through some notes. Okay, let the modulating and carrier signal be denoted as MT and also A cos 2 pi FT. Okay, so MT is modulating signal and this one A cos 2 pi FCT is a carrier signal. Okay, so these two signal apply as input to a summer. So earlier we saw, so there's a summing unit. Okay, so we call it as a adder or summer. So once it goes through, both signal goes through the summer, so it will be combined together. So to form this, so mathematically we can write it like this. So M plus CT, MT plus CT. Okay, so it will generate a signal called V1T. So this signal V1T is applied as input to non-linear device like diode. Okay, so diode also can be used, but there can be some differences in the non-linear device. So the characteristic of the diode are closely related. Okay, so after the passing through the first block here, so it will generate another signal called V2. So that is this formula. So we will get a square law formula. So using this equation. Okay, so we will have K1 and K2 as a constant. And when we substitute this inside the signal, so you will get a new signal like this. Okay, so you no need to worry about the derivation. So you just need to remember the flow so that you can understand. Okay, so this formula you are substitute in this formula in order to get V2T. Okay, so after that you will get this formula. Okay, so the formula is here. So you can see it's quite long. So it's quite long, and if you simplify this, so you will get the equation like in the box. Okay, so once you get this box, so you can see this V2. So based on the previous signal, so you have V2. So then you will pass it to a band pass filter in order to get the modulated signal. So we will see how the thing done. Okay, in the V2T signal, so you have first component, second component, third component, and fourth component. So you have four components inside. Okay, so we read a little bit. The last term of the above equation represent the desired EM wave, and the first three terms of the above equation are unwanted. So meaning, so we just want this part. So we have four parts: part one, two, three, and four. So only these are representing the modulated signal. So the others are just a combination of some signal and also constant. So we can, if possible, we want to cancel it. We don't want to use this. Okay, so what we need to do in order to just maintain this, so we need to have a band pass filter. Okay, so we can pass only AM wave and eliminate the first three terms. Okay, so you can see, so this equation is passed to a band pass filter. So what the band pass filter will do, so let's say your signal is like this. So you have a whole signal. So starting from zero, it goes up, then goes down back. So using the band pass filter, so you only can take signal between one frequency to another frequency. So meaning, so this part and also this part on the right hand side and also the left hand side, it will be removed. Okay, so only the middle part will be maintained, so which we call it as a pass band. So that's why it is called band pass filter. Okay, so you have a band and also you are passing only within the frequency, so frequency FL to FH. Okay, so by passing through this, so after some time, what will happen to this equation? So the first component is cancelled, second component is cancelled, third component is cancelled. So you only will have the modulated signal at the end. So this modulated signal is what we call as a ST or the modulated signal. So we will only use this. Uh, okay, so some words are missing. So it's actually this whole thing K1 AC in bracket 1 plus 2 K2 over K1. So MT bracket cos 2 pi FT. So if you have your notes end out, so you can just write it down completely. Okay, so I think there's some mistake. Okay, so this will be the signal prepare for us to send. Okay, from transmitter to the receiver. Okay, as a EM modulation. Okay, so you can see you can compare the standard equation of EM wave. So this is the standard equation of EM wave. Okay, ST equals to AC 1 plus KA MT cos 2 pi FT. So we have seen this yesterday in the previous notes, the standard form. Okay, standard form without any variables or values. Okay, and this is from previous page. Okay, sorry, page 24. Okay, page 24. So you can see uh, here you are getting K1. So K1 is one constant. So AC is the same, 1 is the same. So Ka is 2K2 over K1. So MT cos 2 pi FCT. Okay, so the other, if you compare with the standard equation, so it is maintaining the same formula. Okay, so Ka is acute sensitivity. Okay, so by comparing the output of the square law modulator with the standard equation of AM wave, we will be getting a scaling factor. So scaling factor is here, the scaling factor is 1, here the scaling factor is K1. So scaling factor for this frequency is, this waveform is K1, and so earlier we saw Ka is the amplitude sensitivity. So Ka for this case is 2K2 over K1. Okay, so this is for square law modulator. Okay, so I have included another question for you. So yesterday I gave you two questions. Try it yourself one and also try it yourself two. So try to solve this also. Okay, so for the square law modulator, the square law device is characterized by V2 equals to V1 plus 0.1 V1 square and band of band pass filter lies between 8000 hertz and also 1200 hertz. Okay, find the parameter of resulting EM signal. So take MT. So the modulator signal or the message signal is 2 cos 200 pi t, and the carrier signal is CT, equals to 20 cos 2000 pi t. Okay, so you need to combine both in order to find. So you just follow the previous step. Okay, so if you can remember the previous step, so by today I will upload the video, so you can listen back in order to get understanding before you solve it. Okay, so try to solve these three questions that I have given, because it is quite important for. So if there's any calculation question that will be coming out for your midterm exam, so it can be coming out in the similar form. Okay, so it's not the same, but it can be in the similar form. Okay, so try to do it. Okay, so we move to the second types of modulator. Earlier we have seen, so it is switching modulator. Okay, so earlier square law modulator, so this is switching modulator. So modulation can be happen as long you can get the modulated signal, so it's already good. So you can use either way. You can use square law modulator, or you can use switching modulator. So it's up to you, because the function is still the same. So you have MT, so you have a carrier signal, you combine it, so you will get V1T. So you apply to earlier square law. So here you are using switching diode. So after that you will get a signal. So you need to use the band pass filter to cancel unwanted components, and you will only maintain the modulated uh, wave. Okay, so it's still the same. So just this middle part will be a bit different. Okay, so similarly we go through a bit. Okay, so if you read, you can understand. Okay, suppose you can understand, but I'll just go through with you. So switching modulator is similar to the square law modulator. The only difference is that in the square law modulator, the diode is operated in a non-linear mode, whereas in switching modulator, the diode is as to operate as an ideal switch. So non-linear mode meaning, so it can have variation. Suddenly it can have new inputs, so it must be able to manage. So if you are applying the modulation signal, you want to get modulation signal from very unstable wave, so then you can use a non-linear mode. Okay, so and if you can get a very similar kind of signal as the input, then you can just switch to diode or switching modulator. So it depends on your application where you want to apply it. Okay. So let the modulating and carrier signal be denoted as MT and CT. Okay, CT here is AC cos 2 pi FCT. Okay, so carrier signal. Okay, so these two signals are applied as input to a summer similar. Okay, so you're mixing MT and CT. You plus both. Okay, summer block produce an output, okay, which is addition of modulating and carrier signals. Mathematically we can write it like this. So V1T is, so MT plus CT. Okay, MT plus CT, so you can get MT plus AC cos 2 pi FCT. Okay, so this is the signal that the first wave. Okay, the signal V1T is applied as an input of diode, so you are applying here as a switching and diode input. So assume the magnitude of the modulating signal is very small, okay, when compared to the amplitude of the carrier signal. So you just assume, okay, you see, so the diode on and off action is controlled by carrier signal. Okay, so this is just a switching mode. Okay, so this means the diode will be forward bias when CT more than 0, and it will be reverse bias when CT less than 0. So as much as possible, we will try to maintain it above 0. Okay, because if it's less than 0, so it will affect the signal. Okay, so it will see, so if it's less than 0, we make it 0. So we will try to achieve only the top part. Okay, so we try to maintain a CT more than 0. Okay, so we can approximate this as so V2T equals to V1T xt. Okay, so based on this, so you can get, so because it's only one wave, one component, so you are getting based on x. Okay, so where xt is the periodic pulse train with time period. So because diode usually it will be, so where is it? It will be on or off. So when it on or off, so it will be either 1 or 0. Okay, 1 or 0. Okay, so you will get a some similar signal like this. Okay, so it will be like a pulse, but it's just will be in the square wave. Okay, the Fourier series represent of this periodic pulse train is, okay. So this is a Fourier series. You will try to apply this inside. Okay, so I'm not going through this. Okay, so similar with the previous one, but here you are using a Fourier series. So because you have a summation, okay, so you are getting, okay. So I'm not going through this. So it's just a derivation. It's just an expansion, and you substitute inside the equation two. So we are more focused on this slide. Okay, so after you solve that equation in the previous slide, so you will get so this will be your final output. So because it's in a Fourier series, so it can be a bit long. Okay, so you can see V2t equals to AC over 2 1 plus 4 pi AC mt cos 2 pi fct. Okay, plus mt over 2. So you can see, so you have a one component, two component, three component, four component, five component, and it's going on because it's a Fourier series. So based on this equation, so which one you think is a amplitude modulated signal out of all these components? So which one is similar to AM wave? Okay, so you can you so which one?
The first one?
Okay, first one. Okay, so for your first one, you can say is having a MT, is having a AC. So you have cos 2 pi FCT. So if compare with the others, so it might have or might not, but which one we will be focusing. So you can see here. So that's the first term. So correct. First term of the above equation represent the desired AM wave. Because when you modulate a signal, so you can have a lot of components. So you only need to take the component that represent the AM wave. So that's the main thing. Okay. So the first term. So this is the signal. So you only interested in the first term. So then the other terms you want to cancel it. Okay, so that's with the help of band pass filter. So you're using band pass filter again. So you'll pass only AM wave. So you need to know the cutoff frequency. So which one is the lowest frequency you want to admit and also the highest frequency. So once you pass to the band pass filter, so it will only take the waveform between that frequency. Okay, so you want to eliminate the remaining items. Okay, so you once you solve this, after you pass through the band pass filter, so you will get like this. Okay, so this is the signal. So st equals to AC over 2 1 plus 4 over pi AC mt cos 2 pi fct. Okay, so this is the AM wave that you'll be using. So you compare with the standard form. So this is the standard form. So you can see, uh, so you have AC here. So you there's a constant. So constant is half. Okay, 1/2. Okay, 1/2. So that's the uh, scaling factor, and you have amplitude sensitivity Ka. So Ka is this form. Okay, 4/pi AC. Okay, so Ka is amplitude sensitivity. So By comparing the output of the switching modulator with the standard equation of AM wave, we will get the scaling factor of 0.5 or 1 over 2. Okay, so 1 over 2. Okay, half. Okay, and amplitude sensitivity Ka is 4 over pi AC. Okay. Okay, so for your exam, so you no need to derive, something like this. So you can straight away use this. Okay, so depending on the information that will be given, okay, so you try to get the form and you only compare with the standard form. Okay, so that's for the AM modulator. So yeah, we have two types of modulators: square law modulator and also switching modulator. So we have seen how both will be working. So almost similar in construction, but in terms of signal and also the cancellation of the component, a bit different. Okay, so we can use this. Okay, so now we will see AMD modulators. Okay, so once you modulate the signal, so you need to have a demodulator in order to split the signal. Earlier, modulator it combined the signal, so message signal combined with carrier signal. Okay, so in demodulator, so the carrier signal will be separated from the message signal. Okay, so that's the function of demodulator. So the process of extracting an original message signal from the modulated wave is known as a detection or demodulation. Okay, so we want to extract meaning separating. Okay, so the circuit which demodulates the modulated wave is known as a demodulator. So the following demodulator detectors are used for demodulating AM wave. Okay, similar like modulator, we have two types of demodulators. Okay, that we will usually use. The first one is square law demodulators. Okay, so name almost the same. A square law, and we have a envelope detector. Okay, so envelope detector. Okay, so we will see square law demodulator first. Okay, square law demodulator is used to demodulate low level AM wave. Okay, so low level. Earlier we have seen. I think yesterday we have covered that. So if you want to when you do modulation, you want to send a signal over a long period. So the message signal will be low frequency, and the carrier signal will be high frequency. You join together, so it can travel along. So here, you are getting uh, the wave after it travels certain distance, it will become low level again. So you need to have a detector in order to separate it properly. Okay, so this is the square law demodulator. You receive the AM wave, so it will reach the square law device. So after that, it will be passed to low pass filter, because we only want to take low signal, low frequency signal. So so from the name low pass filter means it only passing the low frequency. Okay, so then you will get the demodulated output. Okay, so this demodulator contains a square law device and low pass filter. Okay, so the EM wave V1T is applied as an input to this demodulator. So demodulator is here. Okay, so the standard form of EM wave is, so this we know about this. So standard form is AC 1 plus KAMT cos 2 pi FCT. So this is your standard form. Okay, so okay. So we know that the mathematical relationship between the input and output of a square law device is, this is from the previous slides. So we have seen V2 T equals to K1 V1T plus K2 V1 square T. Okay, so this is a standard equation. Okay, standard equation. Okay, so once you substitute this equation inside this equation, So you will get this equation. Okay, so you will get this equation. So when you expand it, so from here you expand further. So you remove all the brackets. So at the end you will get uh, V2 wave, V2 equation like this. So first component, second component, and third component. So you have three components. Okay. Okay. So once you get this, so this is the same input. So actually, if you see, if you expand it, so you will get one component, two component, three component, four component, five component, six component, seven component, eight component. So you are when you expand it trigonometrically more, you will get more components, and you are passing. You only want selected outputs. Okay, selected outputs as a message signal. So you are passing through the low pass filter. Okay, so don't worry about the derivations. So we will uh, have some exercise on this. Okay, on how to do. For now, you just need to understand how the modulator and also demodulator functions. Okay, so in the above equation, the term K2AC square KAMT. Okay, so it's here. Actually, most of the elements are having this component. So this is a scale version of the message signal. So it can be extracted by passing the above signal through a low pass filter and the DC component K2AC square over 2. So you are combining so low pass filter with the DC component. So DC component will remove all this element, and low pass filter will only take a certain frequency. Okay, so we can couple it together in a coupling capacitor. Okay, so this is more on the hardware side. Okay, so once you do that, so you will only get in the standard form. Okay, so the message signal, the standard form. Okay, sorry, I just go behind. Um, okay, so it will be in the yesterday's slide, so I'm not really going through. So maybe later you can check, you can compare. So which element will be similar like the message signal? Okay, so you can check. Okay, so that's one method. Okay, then we have another method called envelope detector. Okay, envelope detector is used to detect or demodulate high level AM wave. Okay, following is the block diagram of the envelope detector. Okay, so you're having a EM wave, so you're passing through the diode, and you have a low pass filter, and it will be a demodulated output. So once you it pass the low pass filter, so it will be cancelled, and only the message signal will be retained. Okay, so I'm not really going through these calculations, so it will be almost the same like a square low demodulators. Okay, the envelope detector consists of a diode and also low pass filter, same like previous. Here, the diode is the main detecting element. So earlier, the square law was the main detector. In the envelope detector, so the diode is the main. Okay, so the envelope detector is also called as a diode detector. The low pass filter contains a parallel combination of the resistor and also capacitor. Okay, so here's the construction. Okay, so the AM wave ST is applied as an input to the detector. So ST you are applying here. So so this is the standard form of AM. So it depends on your signal. Okay, so any questions so far? Anything that
No, doctor.
huh? Nothing? No question?
No,
Yes, sir.
doctor. No, doctor.
Okay, so